theme of this conference. I'm going to be discussing quantum Hall bilayers. People have been studying this subject for a very long time, for more than 20 years. And it was a bit of a shock when I realized recently that I've been involved in studying the system for almost that whole time. And the reason there is some connection to the subject of this workshop is because some of these quantum Hall bilayer systems have properties that are kind of akin to superfluidity. It's not exactly superfluidity, as I'll discuss as I go down the slides, but it seems to be something like superfluidity. And actually, one of the big challenges in the subject is understanding how you can get a state that is, in some sense, almost a superfluid, but not quite, of the type that we'll see as I go along. Let me start by acknowledging my collaborators. First with the students. Noah Ray Ali and Janmin Sun are postdocs, respectively, at Kentucky and Indiana. Stanley Ristai was a student at Oklahoma, has since moved on to a postdoc at Case Western. And then my more senior collaborators are Kieran Mullen, who's an Indiana alumnus, as well as Gantati Murthy and Steve Simon. So Egor asked me to give a sort of a long introduction to the subject, and so actually what I decided to do is give sort of two introductions. In the first one, actually, I'm going to talk more generally about a set of phenomena that go under the heading of quantum Hall ferromagnetism. And the reason I wanted to do this is because this is a very nice language to introduce the idea of textures, which are going to turn out to be rather important in the system. And kind of once I've gotten to set this up, I'm then going to specialize to the case of bilayers. Quantum Hall bilayers are a special case of quantum Hall ferromagnets. And then I'll show you why people think that there could be superfluidity, a kind of Bose-condensation of particle-hole pairs, basically, in the system. And this Bose-condensate has vortex-like excitations, except in this context we call them merons, and we'll see the slight difference between vortices and merons. So what we'll see when I talk about the experiments here is, again, this almost but not quite superfluidity, and people have been looking for the explanation for this. And I'm going to suggest, and a number of people really before me have also suggested, that this order is probably playing a crucial role in the system. In particular, what I'm going to argue is that this order is going to flood the system with these merons, and it kind of leaves behind a network of regions that are coherent, and we can understand some of the basic phenomena by thinking in terms of this, what we call a coherence network. And then in the last part, what I want to do is talk about some more recent, very interesting experiments in which people do transport in what's called a drag geometry, where you put currents in one layer but not in the other, and then you can measure voltage drops either in the drive or the drag layer. And in doing this, it turns out you learn some very interesting things about the merons. And we'll see that this coherence network model gives us a very natural explanation for what's seen in these experiments. And finally, then, I'll summarize. Okay, so in starting this, let me just remind you about one of the basic properties of a superfluid. Classic superfluid is, of course, helium-4, whose superfluid properties are thought to be related to Bose-condensation. And one way to characterize the superfluidity is in terms of what's known as the phase stiffness. And to set this up, we can imagine having a finite-sized system, and then as theorists think about putting boundary conditions across this finite size such that the wave function for the condensate, rather than being periodic, as you might typically do, we can have an extra phase added to this periodic boundary condition. And when you do this, if you're in a superfluid state, what you find is that the energy is a function of this angle theta, and it's a quadratically varying energy, so that this behaves a little like, if this theta is kind of a perturbation, this is acting a little like the system has a kind of elasticity. It was actually Phil Anderson who kind of coined this phrase, generalized elasticity, to characterize this sort of property. And like an elastic system, when you have this kind of behavior, there are low-lying sound-like excitations, acoustic excitations. They disperse linearly with wave vector. In the case of superfluid helium, there's also this famous Rhoton minimum. And in the superfluid case, this is the only low-lying excitation, so that this is one way of understanding actually why there is superfluid, basically dissipationless transport in the superfluid. Okay. So how is this relevant to the quantum Hall system? Well, when we have systems which have a discrete degree of freedom, quantum Hall systems with a discrete degree of freedom, these have a similar type of property. They have a similar type of stiffness. And systems like this are a special case of what we call quantum Hall ferromagnets. Those are systems basically where, in addition to the orbital Landau levels due to the magnetic field, there are also discrete degrees of freedom. So, for example, the paradigm for this would be the spin degree of freedom of the electrons. Now, you might think that that's kind of irrelevant because everyone here knows quantum Hall effect takes place in a strong magnetic field, but that is not the case because if you look at the non-interacting Zeeman energy for the electrons, the energy scale for that is typically very small compared to the electron-electron interaction. So, for example, if there's some energetic reason for minimizing the potential energy of the system, that it would pay not to polarize the electrons, the system will actually do that. In spite of the Zeeman energy, the electrons will not be spin polarized. And there's a number of fractional quantum Hall states where that's known to happen. Other examples of these quantum Hall ferromagnets where we have these discrete degree of freedoms, of course, the layer system, which I'm going to talk about soon. And people have also spent some time thinking about systems when there's a valley degree of freedom. Okay, so now what's the sense in which this is a ferromagnet? So let's focus on filling factor 1. What that means is that I have exactly the right number of electrons to exactly fill a single Landau level. Now, if I have a discrete degree of freedom, and let me for now talk about spin, because it's the simplest paradigm, and we'll also ignore the Zeeman coupling. Let's just take that to be 0. In that case, if I have a spin up and a spin down state, discrete state, then I'll have 2 copies of the Landau levels, one for each spin, but I only have the right number of electrons to fill one of the 2 Landau levels. So I can fill these levels in various different ways, and the simplest way to think about this would be, for example, to put all the electrons in the spin up state, or you can put them all in the spin down state, or you can put them all into some linear combination of them. All those cases, if the Zeeman coupling is 0, are going to have the same energy. And it turns out putting all the electrons in the same discrete state is energetically very favorable, because in that situation, if everything is in the same discrete state, then you can have an orbital state that's completely antisymmetric. That means that if 2 electrons come together, the wave function will vanish, and you do a good job of minimizing the potential energy when you do that. So it's very natural, actually, then, for the electrons to spin polarized, even without a Zeeman coupling in the quantum Hall system. So if you, for example, look at the single particle spectrum in the Hartree-Fock calculation, you'll find that whereas without any interactions, these 2 levels are degenerate, a fairly large gap will open up typically. And this state will be, these states will be completely filled, and these states here will be completely empty. And we can choose our discrete state to be really anything we want. So there's a broken symmetry in this ground state. And that's a situation where we get a spin stiffness. If I make that discrete state vary as a function of position, there'll be some gradient energy associated with that. And we get basically low-lying excitations associated with slow variations in how we polarize the electrons. So there are a number of things we know from the standard ferromagnetism literature. For example, we know that we'll have spin waves in the system, and these will be gapless if there's no Zeeman coupling. And one might worry that whether you have Hall quantization when you've got these gapless excitations. We usually associate Hall quantization with having a gap in the spectrum, but it doesn't take too much effort to realize that this is really not a problem because the spin waves are neutral excitation, whereas what you really need to spoil the Hall quantization is a gapless charged excitation. And it turns out all the charged excitations in the system still have a gap. Now, more interesting than this, which has attracted a lot of attention, are the skyrmion excitations. And in case you haven't heard about what that is, let's imagine that we have a ground state where all the spins are pointing down. So we can create a skyrmion state by, for example, pulling the central spin upward. And now we have to somehow relax the spin from this minority direction back to the majority direction. And we don't want it to happen too fast because if the spin flips very rapidly as a function of position, there'll be a large gradient energy associated with that. So it'll be energetically expensive. So we sort of slowly and continuously have the spin point from up to down. And in doing that, you see that the spin has to pass through the XY plane. And now as I move out in different directions in the orbital plane, you see that the direction of the spin is different in different directions. So if I take a path that goes around the center here, you can see that the in-plane spin actually wraps around by 2 pi. Okay, so that shows us that there's a non-trivial winding here. The winding is a little more complicated for the skyrmion, though, because you can see that if I think about the block sphere, the set of all possible directions that a spin, a Heisenberg spin can point in fact, the skyrmion excitation represents each of the possible orientations exactly once. So this has this winding number, which is known as the Pontryagin index, that tells us that we basically have covered this block sphere exactly once in the excitation. Now, in the quantum Hall system, this situation where we have the spin changing directions, and the spin changing its direction in different ways depending on which direction you go in real space, that's what we call a textured state, and it has a very interesting consequence in quantum Hall context. And the reason for that is that when you have such a spin density, when you have such a texture, you can characterize it in terms of a quantity here. This is known as the Pontryagin density. The n hat is just the unit vector that tells us the direction of the spin as a function of position. And when this quantity is different than 0, it turns out that if you create such a state from a single Landau level, you necessarily have to introduce some physical charge. Okay? So there's a connection then between this texture and a physical charge density, so that's called spin-charge coupling. And that has several interesting consequences. For example, for the skyrmion state, if I integrate up this charge density, that means I'd be integrating this quantity. The spatial integral of this quantity is that Pontryagin index, which I just argued is either plus or minus 1, actually, depending on whether you have a vortex-like or anti-vortex-like orientation for the spins in the plane. So this is telling us then that the skyrmion that I just showed you actually carries physical charge. In fact, it basically carries either a plus or minus charge of an electron. And so that's very important because unlike more normal spin systems, that means that I can inject the skyrmions into the ground state by doping away from u equals 1. Right? If I add charge or subtract charge, if this is the lowest energy excitation, the lowest energy charge excitation, and it turns out that it is, you'll be putting skyrmions into the ground state. So we looked at this a number of years ago. One of the things, since these are charged objects that you expect, is as you move away from filling factor 1, we were considering filling factor 1.2, those skyrmions should form some kind of lattice. And it turns out that the lattice, well, if you think very naively, the first thing you would think is that since these are charged objects, they form a triangular lattice. But you notice you can sort of see these places where the spin is basically pointing out of the plane. If I set up that kind of lattice, I'm going to have a fairly large gradient energy for the spin as I connect nearest neighbors. The spin kind of has to rotate around here, you see, by pi. If I instead set up the electrons into a bipartite lattice, for example, just a square lattice, you can see that there's much less gradient energy on the bond connecting the nearest neighbor electrons, rather the centers of the skyrmions.
Is this charge screen?
Does the charge screen?
Is this charge screen? Because, I mean, if you have Coulomb lattice, it has infinite energy. The charge
yeah, so it's a neutral system. And actually, I will talk about that for the bilayer system in a little bit of detail. But of course, there's a background charge that neutralizes it. Yeah.
What is the energy? Because so if I'm just OCD, models and skyrmions don't interact. So what is the energy of this? What is the expression for the energy of the skyrmion laced in this model?
So this is actually done from Hartree-Fock. We actually just project the system into the lowest Landau level, and then you can figure out kind of what the right order parameters are to put in the skyrmion type of spin texture. And so actually here we have the nonlinear terms for the Coulomb interaction. Okay, so in fact, the energy, most of the energy that you get here really is the exchange energy from the Hartree-Fock. Okay. So there are various answers to that question. If you think about just a single skyrmion, for example, you could ask what sets the size of the skyrmion. In the real, in the real situation where you include the Zeeman coupling, actually here we have included the Zeeman coupling. There's some competition between the size of the skyrmion. The skyrmion actually wants to be very small if you include the Zeeman coupling.
The Zeeman coupling goes to 0, right?
Yeah,
then there must be some high order use.
Right. So but that actually basically it comes from the Coulomb interaction. So the Coulomb interaction wants the skyrmion to be very large so that the charge density will be very spread out, whereas the Zeeman coupling wants it to be very small, and the size of the skyrmion is then basically concerned about the competition. Okay. All right. Now this state actually, this is a very interesting state because you notice the way we've oriented the in-plane component of the spins is kind of radially outward from the center. We didn't have to do that. We could rotate all these in-plane spins by basically the same angle, and we would end up with a state with the same energy. So for example, I could have had the spins all going around like a vortex around in a circle. That means that this is a broken symmetry state. It's got a U1 degree of freedom whose symmetry is broken. And so that, for example, tells us that there will be a Goldstone mode in the system. And we'll see that there seems to be an experimental consequence to that. Let me show you a couple of older experiments to see if I can convince you that these fermions are probably real. One of the earliest experiments was from Sean Barrett's labs back from 1995. He was looking at NMR, looking at basically the spin polarization of the electrons measured using an NMR technique. How this varied, spin polarization of the electrons, and how it varied as you doped away from nu equals 1. So what he found was this very rapid decrease in the spin polarization. And that's very natural if you think in terms of the fermion system, because if I add charge, that degrades the spin, right? That many of the spins want to point in the minority direction, not just one. And that naturally explains why this would fall very rapidly. And in fact, using the lattice system that I just showed you, we can actually get a very nice match to the experiment with very reasonable experimental parameters. Okay, so that's one indication that fermions could be real. Another one comes from this broken symmetry and this extra Goldstone mode that I mentioned. Again, it's the same group really doing experiments here. They looked at the relaxation rate of the nuclear spins. Normally that relaxation rate is very slow because if a nuclear spin goes from up to down, there's kind of nowhere for that energy to get dumped into. But when we break that symmetry with the Sperm lattice, we get this extra low energy U1 mode, which can absorb the energy when the nuclear spin flips. And so that means when I introduce the fermions, I now have a channel for relaxation for the nuclear spins, and we see that nuclear relaxation rate rapidly increase as we move away from nu equals 1. So that's again consistent with having the fermions in the ground state of the system. Okay. All right, so hopefully I've convinced you that we can get fermions in the ground state. That's going to play an important role in what I have to say about the quantum Hall bilayer, or physics like that is going to play an important role. So let me explain what the bilayer is. This is a sort of very standard system for quantum Hall experiments in which you have quantum wells, basically sandwiches of different types of semiconductors, aluminum arsenide and gallium arsenide are the materials of choice. These have different band gaps. In particular, gallium arsenide has a smaller band gap. Now, if we just have the system by itself, the valence band would be completely full and the conduction band would be completely empty. But what the experimenters do is put in some silicon dopants on either side of the quantum wells. The electrons come off these dopants, leaving behind charged silicon atoms in the lattice, and then we get some electrons inside the quantum wells. And so the charged silicon donors are the background that you were asking me about. Okay. So now if we have everything kind of nice and symmetric here, we'd expect to have equal populations of the two wells. I'll also talk towards the end about some experiments where they put an electric field perpendicular to the layers to get more charge in one well and less charge in the other. That turns out to have some interesting effects. And of course, if we're going to go in the quantum Hall regime, we're going to apply a strong magnetic field perpendicular to these layers. Okay, so we can quickly see that there's a connection between this system and the Heisenberg spin system. If we think of, for example, one layer as being the analog of a spin-up state and the other layer as being the analog of a spin-down state, we have a two-state system, just like a spin system. But the fact that the charging energy favors having equal populations in the two wells means that there's something here that isn't present for the SU2 symmetric case of the real electron spin. In particular, that means that if we form states that we describe in terms of spin, we'd like to have those effective spins pointing in the plane so that we have equal probability in the left and right well. Right? So that will balance the charge. So that means that the model that we need to use to describe this system is actually an easy plane ferromagnet. Okay. All right. Now, let me come to explaining why this is relevant to superfluidity. It's basically through a particle hole transformation. So let's adopt as a vacuum, let's consider having all the electrons, let's say, in the blue layer. Okay? So I'll use hole operators to describe changes in the state for the blue layer and electron operators for changes in the state in the red layer. We can then form a trial wave function here, which makes particle hole pairs in the two layers, and I can basically put in enough particle hole pairs that I'll get equal populations of electrons in the two layers. And in doing this, you see that I form what looks very much like a BCS wave function. And you can do calculations of the energy of this wave function, and it turns out to be quite a good trial wave function. It's a very low energy. Moreover, you notice that if we think of this then as some kind of superconducting state, you see that the object that we're condensing is actually a particle hole pair. Okay, so this ferromagnetic state of the ferromagnetic state of this easy plane ferromagnet is, in another language, the same thing as an exciton condensate, a condensate of particle hole pairs. We have a very interesting situation in which all the particles are actually in one of the layers and all the holes is in a different layer. They're not actually in exactly the same space. Okay. All right. The other thing to point out is that we can choose this phase angle here, theta, to be, again, anything we like. As long as I don't make it a function of x, it won't affect the energy of the state. So again, this is a broken symmetry state, as you would expect for a system that has a ferromagnetic ground state. But again, since it's only a U1 degree of freedom, this is like an easy plane ferromagnet. Okay, so if we really want to believe in this state as being some kind of condensation of electron hole pairs, what would be the superfluid response to the system? Well, it would be some kind of counterflow superfluid. If I get currents of the excitons, the particle hole pairs, that means in one layer I've got hole currents, in the other layer I've got electron current, so they're equal and opposite electric currents in the two layers. And that's what I would want to couple to if I want to see superfluid behavior. Just to give you another indication that the system does act like a superfluid, this is actually the first calculation I ever did on this system. You can actually compute for the bilayer using, this is basically like time-dependent Hartree-Fock, this calculation. You can compute the collective mode excitation spectrum, and it looks rather like what you see for helium when you do this. And there's been some later theory where people looked at what happens to this minimum. As you separate the layers, it turns out this minimum will actually touch zero. There's some ideas that this might be related to how you go out of the coherent state if the layers get too far apart. But that's actually also a very interesting but controversial subject. Okay, so we expect then that we might be able to get this kind of superfluid behavior in counterflow. And it actually took a long time for people to actually try to find this in an experiment, because it's very hard to connect to these two layers separately. They're very close together in real space, typically on the order of tens of nanometers. And so it was really Jim Eisenstein who, over a number of years, figured out how to do this. And once he did, one of the experiments he did, one that's most relevant to the counterflow, is one in which he actually passed current in one layer in one direction, and then basically takes the current out of the cryostat and puts it back in the other layer, so that he has equal and opposite currents in the two layers, and then measures the voltage drop down just one of these layers. And that's basically the curve that you see here sort of on the bottom. Near nu equals 1, you can see this dip in the resistance. Okay. So now we can plot that resistance, or equivalently the conductance as a function of temperature. That's this picture over here. You're seeing in counterflow, it seems like that conductance, the voltage drop along the layer, is going to 0 as T goes to 0. Remember, this is 1 over temperature. And this is a logarithmic scale, so it's shooting up very, very fast. It's an activated type behavior. All right. So it looks like we could, at 0 temperature, get superfluid behavior. But you notice something strange, that the superfluidity really, if it's there at all, will only emerge really if we go all the way to 0 temperature, at least as far as we can tell from the experiment. And that's not quite right, because that's not what's supposed to happen, for example, in a thin film superfluid. What you're supposed to have is that the linear response will actually become divergent below the Koslov-Stalos transition temperature. There should be some range of temperature where you have no dissipation in linear response. So this is not doing that. This is some kind of imperfect superfluidity. And that's been the challenge in this field ever since this and some other related observations we're seeing, is how can you get this kind of imperfect superfluidity? What kind of state can do this? Well, the fact that we're seeing dissipation in the system suggests that vortices, right, if it's like a superfluid, then probably vortices are playing some kind of role. But in the quantum Hall bilayers, we want to be a little careful about what we mean by vortices. These objects go under the name merons. Here's a picture I found in somebody else's paper, a very nice picture of a meron. It's very much like a vortex, right, or the spins in the plane go around, but because these are Heisenberg spins, they can also tilt out the plane, so there's no singularity at the core. Instead, what happens is the spin simply tilts out of the plane as you go through the core. And you notice here in this picture it's tilting up, but it equally well could tilt down. And those excitations, whether it tilts up or down, are actually physically different. Because if you think about the block sphere, the directions of the spin that we've actually covered are either going to be the top half of the block sphere or the bottom half, depending on whether it's tilted up or down. And remember now the connection between the spin textures and the charge. If I go on the top half or the bottom half of the sphere, I'm actually going to have opposite charges. So in fact, these meron excitations are charged excitations in the quantum Hall context. They've got either charge plus or minus e over 2, at least in the case of balanced layers. Since these are vortices, if we have a very clean system and we imagine making these low energy excitations, well, you imagine that having vortex-anti-vortex pairs is really going to be the lowest energy excitation. And when you do that, you create what we call a bimeron. So this is a picture of SZ and the SX-SY for a bimeron. And when you set this up, then you have, it turns out, either two charges of plus E over 2 or two charges of minus E over 2. So the basic charge quasi-particle then for the clean system is actually charged, has regular electric charge, regular electron charge to it.
So are those charges on opposite planes or on the same plane?
Well, they're spread out between both planes, actually. Okay, so the charge density.
But then if it's on the same plane, it'll be unstable.
No. The tilt of the spin is actually into the same plane. Into opposite planes. Okay, it's into opposite planes.
So you have plus on one and minus on the other.
It's plus and one minus because they have the same. They actually have the same charge. One is a vortex and one has to be anti-vortex, and I want them to have the same charge, so I have to also flip the direction of the SZ as well as the vorticity to give them the same charge. If that makes sense. Okay. So in this case, one is up and one is down, but you could also consider neutral excitations where they are both up, and that might happen in a region. So that would be a neutral excitation, but that might happen in a region where there's some imbalance in the layer, right? So that the potential one layer is higher than the other. That will happen. I'm going to talk about this sort of thing in a moment. Okay. All right. So the basic physics then that we start to think about is what happens when I have some disorder in the system. In particular, we want to remember that the neutralizing background is due to these silicon dopants. And those silicon dopants are not laid out in any kind of ordered way. There's going to be fluctuations in their density, and that leads to fluctuations in the potential in the bilayer, and also can lead to fluctuations in the difference in potential between the bilayers. And that sort of physics where you have these fluctuations in the background charge, this was actually looked at a long time ago in the context of quantum Hall systems, long before people started looking at bilayers. It was Alexei Efros who started thinking about this. And notice that just the fact that you have these charged dopants not being uniformly distributed, that by itself gives you very large fluctuations in the effective potential in the layer. In fact, you show these potential fluctuations are divergent as the system size goes to infinity. So because of that, the system has to screen these potential fluctuations. And the only way, the basic way it's going to do that for quantum Hall systems is by creating quasi-particles, so that you get puddles of quasi-particles of one sign or the other, depending on whether the potential is high or low. And what Efros showed was that means actually that most of the plane is actually not going to be in the incompressible quantum Hall state. Most of it's going to be puddles of these quasi-particles. But in between you have these strips that are very close to nu equals 1 where it is incompressible. And those strips will actually percolate through the system. And what Efro showed is that's really all you need to have a fun Hall effect. It's not necessary that the whole plane be in the compressible state, only that you have a percolating strip where the system is in a compressible state. Okay. So the question that Gantati and I asked is, now what happens when we have this kind of physics for the bilayer, where in addition to compressibility, you have to think about the interlayer coherence. So our initial thought about this was that because the merons are charged objects, those are the things that are going to be pulled into the system by these fluctuations. And so this is actually an example of this from a simulation that we did, and I'm not going to show you most of the details of the simulation. But basically what we did is put spins on a lattice, Heisenberg spins on a lattice, a finite size system, and then make up a coupling between this Pontryagin density and an external potential, so that acts like basically the coupling between charge and the potential that you expect from in this quantum Hall system. And what we found, we weren't at all surprised, but we kind of confirmed that and the other thing is we did here, is that it'd be very hard to do really a large disordered system. So rather what we did was look at a system that is really ordered. So it's sort of a compromise between the physics of inducing these textures by the potential, but rather than doing it with a disordered potential, we're doing it with a periodic potential. So what we were not so surprised to find is that when you make this potential amplitude large enough, you indeed form these basically meron excitations, and as you turn up the amplitude of this potential, you're going to get more and more merons in these puddles. So we get in these pictures we have two meron-antimeron pairs per puddle. In the previous one, it was one meron or antimeron per puddle. Okay. So anyway, so this sort of makes sense then that we can sort of go through different first-order transitions as we change the potential and put more and more of these merons into these puddles, which will ultimately become compressible states, compressible regions in the plane. Now, I have less time than I would like, so I'm actually... yes. Sure.
Oh, we're never speak on.
Oh, we're not strict last time. Okay. So I was just say a couple of things then about this. I'm not going to go over all the things that we figured out about this periodic model, but there are a couple of interesting things. One thing that you can convince yourself is that when you're right near one of these transitions between having one number of merons per puddle and a different number, the Koslov-Stalos transition temperature actually drops to 0. Right at it's actually a first-order phase transition, right at that phase transition. Another thing we found by looking at the excitations around these ground states is that when you get near a transition, even though they're typically not typically they're first-order transitions, nevertheless you find that there's an extra collective mode that comes down, doesn't quite touch 0, but can get quite low, and this might have some relevance to dissipation. This might participate actually in dissipative processes in the system, and that's actually something we're still working on. Okay. So let me now kind of come to the model as we think it should be applied to the quantum Hall bilayer experiment. So now we have the system of puddles where we have many meron-antimeron pairs. Some of those meron-antimeron pairs are likely to straddle basically these incompressible strips between the puddles. So these blue regions are basically both incompressible and also the interlayer coherence is going to be strongest in those regions. In particular, when we go to these sort of nodal regions here, which are basically around the saddle points of the potential, there we expect to sort of have the largest regions of phase coherence. So our idea was to focus kind of on these incompressible regions, and these regions where the phase coherence is very strong, and kind of think of it as a network. So a bunch of one-dimensional links that are hooking up these nodes. But keeping in mind that from these puddles, we might have merons or antimerons kind of able to hop back and forth across the links. Okay. Our key assumption here is that the disorder is actually strong enough in the sense that at any finite temperature have these vortices unbound. So this is actually kind of a vortex glass kind of model that we have in mind. And there's some normalization group calculations and simulations that support this possibility. Okay. All right, so let's see if we can understand in this kind of model what might happen, for example, in counterflow. So counterflow is current in at one end, current out at the other. Right? If I want to think of it as kind of a Josephson network model, how would I set up this current pattern? Well, one way that I found very convenient to think about this is to think in terms of the phase stiffness of the system. So where I started this beginning of the talk. So now we've got these links here, and I've shown these sort of hatched area arrows, kind of showing what happens, showing us what happens when we have Meron-antimeron pairs that straddle the links. And when we want to set up a counterflow current, what that would mean in the Josephson network is I'm trying to impose a phase twist across the system. Right? So if I make the phase angle of the Josephson network different at the two ends of the system, and then if I sort of put a torque on the system in this way and there's a torque back on me, that's the situation in which I actually have a superflow. Right? As long as I have to provide that torque, there should be some superflow across the system. And that's equivalent, putting in that torque is equivalent to trying to put in some extra phase fronts into these links. So links like this, well, there's no problem. This phase front will probably annihilate a phase front there. But links like this, we're trying to crowd the system with extra phase fronts, and the system, I'll get the harmonic response from the system trying to do that. And the only way that response, that harmonic response can be relaxed if somehow these phase fronts annihilate so that the new phase fronts can come on in. Okay. So the microscopic way that that would happen is if we remember that the endpoints of these phase fronts are actually really Meron and anti-Meron, right? Vortex, anti-vortex pairs. So what would have to happen is that a vortex would have to hop over a link and annihilate its partner. That would eliminate one of these overturns, one of these 2π overturns, and leave room for the next one to come in. And so when that can happen, if that kind of relaxation can happen, that means that that the torque that I had to put in to twist the system will relax over time, and then I have to keep turning the system in order to keep the superflow going. And in doing that, that means these phase fronts are coming in, and so that means that the angle, the U1 degree of freedom in these links will actually be turning as a function of time. If that happens, the Josephson relation tells me that there's some voltage drop, and if you think about that, that immediately means that there'll be a voltage drop parallel to the direction of current in either of the layers, and so we get dissipation. Okay. And the interesting thing is that the limiting step here in this response is an activation barrier. Right? When one of these vortices, the vortex has to go through this region of coherence. It'll have a high energy until it gets to the puddle region, where the space stiffness is spoiled. And so the activation energy that we are seeing then represents how much energy it takes to push one of these vortices into this incompressible. Okay, so that's the basic idea of why we think that you get this kind of response, this kind of linear response that's seen in the experiment. All right, so in the remaining 20 minutes or so, I guess, let me talk about the effect of interlayer bias, because this set of experiments, I think, more than anything I talked about, really shows in a very nice way that there really should be a connection between, basically a connection between the spin textures and the physical charges of these objects. So we'll see why from the results of these experiments. So people have known for some time that if you bias the bilayer, that in fact you can get sort of an interesting effect that the coherence seems to actually get increased if you don't have equal populations in the two wells. There was actually some theory on this from the late 90s that Alan McDonald and Yogesh Joklikar did. And then there was some experiments more recently that Jim Eisenstein did in his lab that confirmed this tendency for the coherence to actually be enhanced by interlayer bias. So what happens when we have this interlayer bias is that this effective spin, if we do this in the ferromagnet description, and the spin description, this n sub z is no longer 0, as we had, on average, as we had for the unbiased case. Now, somewhat later, there were some experiments out of von Klitzing's lab where they looked at effects of interlayer bias, but they did it in a very interesting geometry. Rather than doing counterflow experiments, they did drag measurements. That means that the current is going in, basically is flowing in just one of the two layers. And then you can measure the voltage drop in the drive layer or in the drag layer. It turns out you get different results for those two different cases. What they find is that if you measure the voltage drop in one layer or the other, you get an activated behavior. You can measure the activation energy for those two different types of experiments. They find a few things. So this is just showing you results, not showing you sort of the analysis in between. they find that the rough scale of the activation energies, first of all, is not very changed by the fact that you imbalance the layers. But the activation energies for drag and drive layers are different, and they behave in rather different ways. So if we look at the activation energy associated with voltage drops in the drive layer, that's the squares here. And this is for one layer, drive in one layer. This is for drive, the drive layer being one layer, the open squares for drive layer being the other layer, as a function of bias, right? The difference basically in densities of the two layers. So you see there's an asymmetric behavior here, right? Basically, if I just look at one of them, depending on whether the bias is in towards the drive layer or away from the drive layer, you'll get either a decrease or an increase in this activation energy. On the other hand, if you look at the drag layer, there's a roughly symmetric behavior. So very dramatically different. And this is actually really quite a mystery because, and there's a number of years actually, well, it took us a few years to understand what could be going on here. Because if you look at this very naively, the fact that I have different activation energies, the sort of most naive interpretation of this is that there are just different quasi-particles for different layers. And that doesn't fit into this picture of a coherent bilayer at all, right? If I have interlayer coherence, there's one type of excitation, we think it's the vortex type of excitation, that are relevant, and the activation energy associated with one of those vortices, you would think that's the only activation energy you see, and it wouldn't matter whether you're probing the drag layer or the drive layer. And in my own discussions with the various people working, not with von Twiss himself, but with the various people who did the experiments with him, I think they got rather, how would I say, they began to become rather pessimistic that there really is coherence in the system, in spite of what's seen in the other experiments, because one couldn't really understand this, and they didn't see any other way to understand this. What I want to show you is that, in fact, this behavior is very much consistent with this coherence network model. But you have to pay attention to what's really happening to the merons in order to understand what's going on. So the first question let's ask is, why could we have more than one activation energy? And that's actually pretty simple to understand. So remember that we have different kinds of merons. Again, we have some that have their core spin pointing up and others that have their spin at the core pointing down. If I put an interlayer bias, an electric field pointing basically perpendicular to the layers, then whether I have the core spin pointing up or down is going to make a difference, right? The symmetry between the two layers is broken if I have an electric bias between the two layers. So there's no reason to think that the two types of merons are going to have the same activation energies. They surely would not. Moreover, that's not the only thing that changes when you put in bias. And the second point is actually more important. It turns out that you have then more than one type of charge. Because now, in the ground state, if I've got my spins now not pointing in the plane, but they're actually pointing out of the plane, they have some component of n sub z. So that means the ground state configuration would have its spin basically somewhere along a red line like this that's not on the equator of the block sphere. So remember then, we have these relations between basically how much of the block sphere is covered and the charge of the excitation. And so some of the excitations are actually going to have a charge of magnitude, it turns out, to be the density, the relative filling factor of the bottom layer, and two of the others are going to have their magnitude be the relative density of the top layer. So we have two different magnitudes of charge for different types of vortices. So both of these suggest that we should have different activation energies depending on what kind of vortex is actually hopping across a barrier. So we tried to estimate this using Hartree-Fock. The way we did this was actually to set up a lattice of vortices and anti-vortices and then put in a potential barrier that basically only half of these vortices actually see. And then, so we computed the energy of the state in Hartree-Fock, and we did it in two cases. One where we had these merons sitting right on top of a barrier, and another where we kind of shifted the position of the merons so that they would be off the barriers. So one is a high energy configuration, one is a low energy configuration. And then you take the difference, and that gives you a measure of how much energy it takes for a meron to cross the barrier. And then we had to put in some kind of fitting parameter. So what we did was take the experimental value of the activation energy for bias equals 0, and that gave us the effective height of the barriers we needed to use. and then computed everything from there. So this is the result that you get. Basically, the crosses are actually the result for merons hopping of one particular sign of charge hopping over the barrier. The red dots are actually basically the same calculation for the other sign of charge, and if you think about it, they have to actually be symmetric. And so if we look at just one of these type of merons, we see it's very natural for them to actually have this asymmetric behavior. So we get basically the correct trend. Our slope here is a little bit smaller than what's seen in the experiment. It's not so surprising because this is a bit of a rough model. All we've actually included is kind of an electrostatic effect for crossing the barriers, but there should also be some effects on the spin stiffness that we haven't included. So that would be very hard to include sort of quantum fluctuations in the spin stiffness. But anyway, this shows us that our order of magnitude is roughly correct. But it still doesn't answer the main question because, okay, so now we have the possibility of more than one activation energy, but what you might think, again, if we have several types of merons in the system, all of which could give you dissipation, you would think that just the lowest activation energy would be what you see in the experiment at the lowest temperatures. And you would think for both layers, probably you should just follow a curve that sort of goes from here to here. And neither of the results look like that. Okay. So why don't we just see this lowest activation energy? So we need to understand in more detail how the motion of the merons actually generates voltage drops in each of the layers. And so this was actually rather simple for the case of the unbiased layers because we could take advantage of the symmetry between the layers. What the Josephson relation actually told us about, since the coherence phase angle is actually telling us about interlayer coherence, if that phase angle is changing as a function of time, that's actually related to the interlayer voltage. But then the symmetry between the two layers tells us that if I know something about how that interlayer voltage changes as I move down the sample, I can infer what's happening in each layer separately, because I know basically that they have to have equal and opposite voltage drops. In the bias layer, though, I lose that symmetry. And just looking at the Josephson relation for interlayer coherence is not enough to tell me what the voltage drops are going to be. So we puzzled over this for a long time, and eventually one day hit on the right way to think about this. We actually need to use what's called a composite boson description of the quantum Hall effect. So some of you may have heard of this. This also goes way back to relatively early days of quantum Hall effect. And this uses basically ideas that are relevant to anyons and singular gauge transformations that allow you to transform bosons into fermions, fermions into bosons, or really to objects which have any statistics that you like that are halfway in between fermions and bosons. And the basic idea is actually very simple. So we know, of course, that we get quantum Hall effect for a system of fermions in the magnetic field. What these guys thought of is what happens if we think of our fermions as, instead of being fermions, we can think of these as being kind of a composite boson. The particles themselves can be bosons, but we'll imagine that there's an infinitely thin solenoid attached to each of these bosons with some magnetic flux threaded through. And if you put exactly one magnetic flux through each of these bosons, well, then if I interchange the bosons along with their magnetic flux, you'll actually get the right minus sign that you expect for fermion, except it's not the exchange statistics that give you the minus sign, rather it's the Aronoff-Bohm phase from the flux going through the particles that gives you the minus sign. And both of these should be valid descriptions of the system. But what's very interesting here is that since we have one flux quantum for each particle, if we direct that flux quantum opposite to the real magnetic field, then if we do mean field theory at nu equals 1, at the mean field level, this sort of fake flux will exactly cancel the real magnetic flux, so that at the mean field level, the system is actually a system of bosons with no magnetic field. And so there, you might say, well, the ground state should be a Bose condensate. And that gives actually a nice qualitative description, it turns out, of the quantum Hall effect. And that's really what these guys pointed out back then. So now these charged quasi-particles then in this description actually become like, well, they become like magnetic flux quanta, right? If I make charged quasi-particles, those are vortices in this Bose condensate, And because because these quasi-particles have charge, since there's magnetic flux associated with the charge, if I make, for example, a quasi-hole, I'll get some real magnetic field passing through that quasi-hole, right? Because I sort of lost some charge density, which was supposed to be canceling out the real magnetic field. Right? So now, this vortex excitation, which is also a charged excitation, we apply a current. This is, everyone here I think knows about this. Apply a current down the sample. That's actually going to put a force, right, a Lorentz force, on the quasi-particle. And it's then dragged perpendicular to the current. And then Faraday's law tells us that that will give us a voltage down the direction of the current, and we get dissipation. So that's how these guys describe dissipation in a quantum Hall effect. And it's very similar in certain ways to what we were really using for the interlayer coherence, for vortices moving in the interlayer coherent system. But we have to be very careful. The sense of the thing that's Bose condensed here is actually different than what is Bose condensed in the interlayer coherent system. Right? This is actually the charged particles that, in this case, have condensed. So now we can apply this idea to the bilayer system. And we have to keep in mind that now, in this description, the system is condensed in two senses. It's a bunch of bosons living in a bilayer. We have interlayer coherence as well as Bose condensation of the charge itself. All right? So that means that if I put current in the layers, there's going to be two, on a meron, there's going to be two sources of force on it. There's going to be the force through the fact that the charge has some flux associated with it, that Lorentz force, and that's tied to the total current through both layers. But then there's also the Magnus force due to the fact that we have this interlayer phase vorticity in the meron. And so you notice here that this force due to the total current is tied to the charge of the vortex, whereas the charge of the object, whereas the force due to counterflow is tied to the vorticity. This S is either plus or minus 1 is the vorticity of the object. Okay. So when we put those two forces together, we get a very simple and interesting expression then for the force on one of these merons. And so now we can look at what happens in counterflow, right? I can put different currents in the two layers and ask what happens to the vortices. So let's look at the drag situation where I put only current in one layer. So let's say all current is in the top layer, the bottom layer has 0 current. Right? So this is 0. So now this is what I have left for the force. The force will depend on this coefficient. But now remember, there is this spin-charge coupling, right? The charge on the charge on the different vortices comes from this table over here, and this this vortex or anti-vortex would be S equals plus or minus 1. So it turns out that 2 of the 4 vortices will have no force on them. The ones with their spin polarization pointing up, when the current is in the top layer, the ones with their spin polarization pointing up actually have no force on them. It's a little bit of unintuitive, but that's what comes out from this calculation. So that already begins to point us in the right direction. That shows us when I do a drag experiment, because of this exact relation between the spin and the charge, when I do a drag experiment, I don't probe all the vortices. Only the ones that have the polarization in a particular direction are going to be pushed through in the drag geometry. Okay. All right, so the last thing then is to think about the voltage drops when one of these two types of vortices is moving through the system. So there are two pieces to that. Remember, there's this interlayer phase angle in the vortices. So that tells us something about the interlayer voltage drop. In this expression, there's a few pieces. This U is the average velocity of the vortices, which have to hop over these barriers. The S, again, is the vorticity of the ones that are moving. And then this NS, and the S here is the vorticity. The sigma is whether the polarization is up or down, and then the Y0 is some distance between two probes where I might be measuring the voltage drop. The delta V here is then the voltage drop between 2 points along the layer, a point at some position at the origin and a point Y0 away. And this particular contribution then, since this has to do with the interlayer phase angle, this actually only tells me about the difference in voltages. between the top layer and the bottom layer. So that's not going to tell me by itself what happens in just one of the layers. But then we have to remember the fact that this vortex also carries effectively magnetic flux. So that's going to give me a layer-independent voltage drop. So that gives me an expression that looks like this. That's charged rather than, it's tied rather than to the vorticity, it's tied to the charge of the object. And finally, when you put these two things together, what you discover is that if I've got currents only in the top layer, I will not see any voltage drop in the bottom layer. Okay? So, so that gives us a picture that is almost what's in the experiment, not quite. What this is saying is that if I put the current in and the current out, according to the model I just gave you, I would see a voltage drop only in the drive layer. I would see no response in the drag layer. Now in the experiment, we see different vorticities for the two, different voltage drops for the two layer. And I don't know if I remember to say so, the voltage drop in the drag layer is much, much smaller than the voltage drop in the drive layer. So in that sense, this is kind of similar, except as I said, you do see some voltage drop in the drag layer, and it's got an activation energy that's different than the one in the drive layer. What this shows us, though, is that since we're only probing one kind of vortex, what we'd see is this kind of behavior then in the activation energy as a function of imbalance in the drive layer. That's exactly what was seen in the experiment. So then the final question for us to answer, and just hitting the end so I time this well, is what happens when we look at the voltage in the drag layer. How come there is some voltage? So our explanation for this is that probably what's going on is that the merons are not always unpaired. Probably we do have some bimerons, vortex-anti-vortex pairs. And when I've got the current pushing one of the two objects in the bimeron, the whole object will be pulled across the barrier. And the activation energy to get across this barrier will likely be whatever is the maximum activation energy is, or the maximum barrier of these two objects as they cross the strip. You'll notice I've sort of drawn this so that the objects are somewhat bigger than the incompressible strip, and our estimations actually of the size scales seem to say that's the right thing. The incompressible strips actually should probably be smaller than the merons themselves. So if we're only going to get the maximum of the two, then we expect to get something that looks like this for our voltage drop. And again, that's the kind of shape that they see in the experiment. So the message from this whole story here, is that, in fact, there are really two messages I guess I want to get across here, is that we see from these experiments that there's a fairly direct confirmation of this relationship between spin and charge. The spin-charge coupling that's special to the quantum Hall system. We get these shapes for these activation energies because they're tied together so precisely. The second thing is this actually tells us a little bit about what we should expect to happen if cleaner samples could be made so that this incoherence, so the coherence isn't so nearly spoiled. In particular, if we have a cleaner and cleaner sample, we'd expect more and more of the merons to be paired up like this. And as more and more of these objects become relevant to the system, what we'd expect to see is a larger and larger voltage drop in the drag layer. And if we could go all the way to the limit where everything is paired up and there are no unpaired vortices, then we'd expect if we measure voltage drop in the drag layer and the drive layer, that we would see exactly the same result. And so that this kind of experiment can be a direct measurement of how close you really are to having a truly coherent state. What this is basically saying, the experiment seems to be saying, is that we're actually not that close. We're just barely starting to see the effects of interlayer coherence in the system. And it's probably because disorder is fairly strong in the systems. So I guess it's time for me to stop. Let me sort of put up my summary here. What I've tried to argue is that we can think of this bilayer nu equals 1 system as an exciton condensate. Disorder induces, we think, these meron-antimeron pairs in the ground state. It spoils the superfluidity, but we can understand why we're coming close to something that's superfluid in its response using this coherence network model. We saw some interesting results in the biased system, and we see that if we marry basically the coherence network model to this idea of describing quantum Hall effect in terms of composite bosons, we're able to really understand what goes on in those drag experiments. So this is basically the papers that have the various pieces of physics that I just described to you. So I'm going to leave it there, and thank you for your attention.